When an industrial plant starts up, a rigid 16-inch steel pipe spanning a 20-foot gap becomes a dynamic object. Engineers must accurately predict exactly how and where the piping will move once the internal temperature and pressure spike. Pipe stress analysis provides the mathematical framework to calculate these invisible forces, ensuring a multi-million-dollar facility doesn't tear itself apart from the inside out. Before analyzing how a pipe moves, we first have to build the physical baseline. The mandatory first step of any piping design is calculating the exact wall thickness required to safely contain the internal fluid pressure. This equation from the ASME B31.3 process piping code determines that minimum thickness. The inputs in blue, like the design pressure and the outside diameter, are specific to the plant's operational data. The variables in orange, such as the material's allowable stress and the temperature coefficient, are fixed values pulled directly from the codebook tables. Once we calculate that minimum required thickness, we add a specific safety buffer, a corrosion allowance, to account for the metal wearing away over time. This final number dictates which standard, commercially available pipe size to purchase. Sizing the pipe for pressure yields a heavy, fluid-filled physical boundary. The subsequent engineering challenge is determining how to safely hold that weight in the air. To keep the piping suspended, engineers use a variety of specialized supports. The two most distinct approaches are absolute rigid restraint versus simple vertical resting. Looking at the left side of this diagram, we see an anchor. An anchor completely locks the pipe in place. It arrests all movement across all 6 degrees of freedom, blocking any axial, vertical, lateral, or rotational shifts. On the right side is a Y+ vertical support. This acts exactly like a table. It only pushes upward to carry the heavy dead weight of the pipe, the internal fluid, and the exterior insulation, forces that engineers classify as sustained loads. Notice there is no clamp holding the pipe down from above. Misidentifying how these supports function causes localized sagging. Worse, it shifts massive structural burdens directly onto sensitive connected equipment, like pumps and vessels. That risk materializes the moment the plant enters operating conditions. When boiling fluid begins to flow, it immediately disrupts the initial static weight assumptions we made at room temperature. This digital model shows a standard 90-degree pipe corner. When we introduce a 500-degree Fahrenheit fluid into the system, the metal naturally heats up and expands linearly. Because the pipe's expansion is restricted by the corner geometry, it seeks the path of least resistance and aggressively bows upward. Because the Y+ support provides zero downward restraint, we see a phenomenon known as liftoff. The upward bowing of the pipe creates a physical air gap, completely separating the steel from its resting place. Thermal expansion stretches the steel and completely changes the physical geometry of how the entire piping network is held up. The danger of liftoff is that the dead weight of the pipe hasn't disappeared. The Y+ support is now mathematically inactive. As a result, that heavy sustained load immediately drops onto the nearest fixed anchor, causing the local stress levels to spike. This abruptly transferred deadweight load attacks the rigid anchor, which was likely never designed to hold the combined weight of the entire span. This specific scenario is a primary cause of structural failure in high-temperature systems. Let's test this concept. This schematic shows a boiler connected to a pipe segment. The pipe is locked firmly at anchor A, rests freely on a Y+ support at point B, and is locked again at anchor C. During a 400-degree operating test, the hot pipe expands, bows slightly, and lifts 1 full inch off the Y+ support at point B. Here is the challenge. For the final ASME code sustained load safety test, which of these 3 supports must be included in your mathematical calculations to prove the system is safe? The correct answer is that only anchors A and C carry the load. Support B is removed from the equation entirely. The logic dictated by the code is straightforward. If a pipe abandons a Y+ support during the hot operating case, that support provides zero help carrying the deadweight. Therefore, it must be completely deleted from the final sustained load calculations. True system safety relies on evaluating this worst-case geometry, a structural state created by the pipe's own heat-induced escape from its intended supports. We can synthesize this entire engineering workflow into an official 3-step ASME code-compliant design checklist, as shown here. Step 1 establishes the pressure boundaries by sizing the pipe. Step 2 requires you to simulate the high temperatures to find exactly where the pipe naturally moves, specifically looking for thermal liftoff. Finally, Step 3 is the ultimate test of structural integrity. You must rerun the sustained deadweight calculations with those lifted supports marked as inactive, ensuring the remaining anchors can survive the transferred weight. Verifying the strength of the steel is only the beginning. A safe design requires predicting exactly where the pipe will choose to rest when the heat is turned on.